So welcome to my Nsight tutorial video. I've loaded up my homemade graphics engine into Visual Studio 2017. I also have Nsight 5.3 installed. Let's get started. So I will start a graphics debugging session. I'll wait a bit for Nsight to start up. So the application is now ready. Let's load a simple scene. Also a skybox. And probably this animated model right here. Let's scale it up a bit, like so. Okay. So I want to capture this frame. So this frame. I want to capture this frame by pressing Ctrl plus Z and space. So we are presented with a most notably a timeline on the bottom of the window. We can scroll through it and see every graphics event. We are also given a small widget by Nsight with some buttons. Most importantly, this serialize button. You can save the capture which you are performing to disk to load it later. We have also wireframe mode for geometry wireframes to be visualized differently. Usually just use the animated one. We also have a render target selector. So for example, we are rendering now the main scene, and I'm rendering to multiple render targets here actually, and I want to select the second one. The first one was the color buffer, and this is a normal and the velocity buffer combined into a single render target. We also have a depth buffer and the stencil buffer, and this is the color buffer. So on top of the timeline there is another sort of timeline indicating my user ranges, which I have set up from my application code. But we can visualize these ranges better by going back to Visual Studio, and here's our other timeline window. Actually this is called the scrubber window, and so in the timeline window we have the draw calls and the dispatch calls. It is color coded just the same way as it is on the replay HUD. The blue lines, which are most frequent ones, are the draw calls. These are rendering geometry to the screen or some off-screen buffers. There are purple lines, which are compute shader dispatches. These are performing some other work on the GPU, not necessary graphics related work. And there are some yellow or orange lines, which are update sub-resource calls, which are updating GPU memory buffer. There are finally the green lines, which are render target or depth stencil clears. So let's get back to Visual Studio and the scrubber. We can have our timeline displayed differently. For example, this is the GPU timescale viewer. We also have the event ID, which is the default for the replay HUD. So there is also the CPU timescale and GPU timescale. The CPU timescale displays the DirectX 11 API calls and their timing on the which incurred on the CPU. So as you can see, the whole frame was rendered on the CPU within 1 millisecond. Actually, it is just 600 microseconds, and just a bit more than a half a millisecond. But this is only the CPU timescale. So these are only the API calls that are dispatched to the GPU, and the GPU will actually work on these some much more time, at least in this application. So the GPU time scale, this is taking much more time than the CPU. It is displayed here as 10 milliseconds, but actually if I view the replay HUD, my profiler shows that it was done in 8 milliseconds. So the captured frame was probably slowed down by the Nsight debug attachment, but we can visualize the timescales nonetheless. So I have some performance markers set up here. As I mentioned, I call these from the application side. There is an call for an ID3D user-defined annotation, and it has a begin event and an end event function. And the begin event, you can define your own strings to be displayed on this debugger, which is very helpful if you want to debug specific draw calls. You can just select this range and select the appropriate draw calls that you want to inspect. So to inspect a draw call, you normally use the API inspector window, which is there by default, but if it is not, then you can call it down by this menu. So this one. There is a separation between the graphics pipeline and the compute pipeline. So the graphics pipeline goes down like this. So first is the input assembler stage, which assembles your vertex data, vertex buffers, combines it with the input layouts, and interprets the data for the vertex shaders. So then the vertex shader executes. For each vertex, a single instance of the shader is evaluated. Then there are some inactive stages right here. The whole shader and domain shader are for tessellation shaders. The geometry shader can add more vertices, primitives to the render pipeline on the GPU, or remove them from rendering. The stream output stage is so it can manipulate vertex buffers. For example, you can do skinning in a geometry shader and stream them out to another vertex buffer. And there is the rasterizer state, which is a state before the pixel shader, and you can view each of the according states. The pixel shader window is quite similar to vertex shader window, and the other shader windows too. So a shader stage window displays the current shader resources. You can view shader disassembly right here, and the description of the shader resources is right here. Below that, you can see the constant buffers, samplers, and the shader input and output parameter descriptions. The most helpful thing here, I think, is the viewing of the constant buffers. So the shader right here, if you view the disassembly, so this is the assembly of the intermediate shader, and on the top, if we have debug information enabled, we can view the constant buffers which this shader uses. And if this shader uses constant buffers, these get named here in all the constant buffers. So if we have a named constant buffer right here, for example, this material constant buffer is oops, I have some problem viewing this because of the space. So yes, in the material constant buffer, we have some properties, for example this base color, and we can see the values of it, which is a white color, and some other material parameters. We can also view resources, like the buffers are also resources, and textures, for example these. We can view raw data of the buffers and all different resources. So for example, this material constant buffer, I click on this buffer 35, and this brings me up the resource window. So in this resource window, I can view raw memory data for this buffer. I can interpret this data as different kinds of values. So I want to interpret this as floating point values. Oops, it doesn't refresh. Maybe if I switch buffers or minimize the window or something. So buffer 35 is my constant buffer. I can interpret data, and I know that the first color value was 4 floats, and as we can see, this is the white color as viewed as raw data. This is another vector below that, and the following floats are just those other material parameters. We can also view this as one column if we would like so. So in this resources view, we have buffers as well as textures. We can view just the textures if we want by filtering out the buffers. At default we have both enabled, but I can disable the buffers here, so all of them are just textures. So for example, an object texture would be this. This is a texture of the windmill. We can view MIP levels and everything of it. If we hover the mouse on top of it, we can see the pixel values, which is very helpful. We could also see pixel history for a given pixel and debug the shader that created this pixel, but it is not available, unfortunately, on my GPU, which is a NVIDIA GTX 1070. So probably in the future it will be supported, or at least I hope so. So we can also view render targets and default textures here. For example, this is a render target, and below the render target there are available revisions, and this is an interesting view because you can see an event which modified this surface, this resource, is displayed and captured as an event here. So yes, this resource have multiple states, or this resource has even more states, because more events modified this. So as you can see, some events generated multiple states of this texture, and we can sort of rewind time and look up which event modified which part of the surface. We can also view a surface by raw memory, but we have to carefully interpret the data as we like, because actually there is no automatic interpretation like with constant buffers. So below these resources you can find the available views that you have created for this resource. So again, this is also very helpful, and by clicking on it you can just view that view. So let's get back to the main thing. So we had had a look at the API inspector. There is there is also output merger stage, which has all the state descriptions associated with this stage. We can let me find the draw call which modified the output merger. First, I'm gonna zoom out by control and scrolling with the mouse. So, for example, these draw calls are the my main scene rendering and shading draw calls. So, for example, this draw call did modify the output merger. There are 4 render targets, or 2 render targets and a depth stencil target bound to this stage, and we can view these as resources, as discussed earlier. Also resource descriptions, blend mode description for the resources. It's all very helpful. So let's see, for example, a compute shader stage. This is a compute shader which performs light cooling for my forward plus or tight forward rendering pipeline. So this is a compute shader detached from the rendering pipeline, but it renders to some textures and buffers, or rather not rendered, just fill the memory, because compute shaders are not rendering shaders. So all the information which we had with the vertex shaders, pixel shaders are here as well. So there is another important window, the geometry window. Let me first scroll to geometry rendering draw call. For example, this is my main scene, one of our main scene rendering draw calls. See on the graphics as the frame HUD. So yes, these renders the trees with instance draw calls, rendering 33 instances with a single draw call. And so the geometry window would display your mesh, one of your mesh in a 3D viewport, but this is actually not working for me at this time, because it worked for me for some time, but I rewrote some parts of my rendering pipeline and it stopped working. I already submitted a bug report to the NVIDIA team, and I'm waiting for a fix which will hopefully arrive in the near future. So it is a very good window. You can select different things, view different vertex buffers and different coloring, but it's pretty self-explanatory and easy to play with, but not in this application, it seems. It's also indicating that floating point special detected in vertex data, which is a helpful feature, because if you look at the memory, you can easily detect errors in your vertex buffers. But actually, in my case, this whole vertex buffer, every vertex buffer is a big error. I've actually double checked this. My vertex buffers are completely fine, because if I view the raw data, for example, this I want to view this vertex buffer. So I've got the positions in a separate vertex buffer, and it is displaying faulty data right here in the interpreted vertex buffers. So let's see the raw buffer quickly. So on the input assembler stage, I have got my position input layout semantic, and this is the vertex buffer associated with it. It's a floating vertex, so it's a float 4 vertex buffer. We can view it as raw data, but interpret it quite easily. I just select 32-bit float, and the columns 4 is perfectly fine because its position. The first 3 elements are actual word space positions. The last element is a weight used for wind animation, procedural wind animation, and packed into this vertex buffer as well. So as you can see that this vertex buffer has correct data, or at least not so bad as we could see in the geometry window. The geometry window is also nice because, well, at least if it was working for me, it would be also nice because it correctly interprets your memory data, and if you provide an appropriate input layout, so it can be easy to debug if it would be working. And another important window is the API statistics window, which you can bring up here. This displays your API calls for this whole frame grouped together. So as you can see, I have 340 draw calls, and these are my draw indexed draw calls, which of there is 131, and also draw indexed instance indirect draw calls also count for that, and the regular draw calls like draw indexed are also count for that number. So yes, you can see that draw calls are GPU timed, and other calls, and by the way also dispatches are also timed for the GPU. So GPU time for these is relevant, but CPU time is mostly not. You can have many thousands of draw calls in DirectX 11. It is not much of a CPU overhead at this point, but the most CPU overhead would come from all the other different state setups and these map unmap calls, which are memory allocations basically. In most graphics pipelines, these are the most responsible for CPU time on the API side, and the draw calls are on the GPU side are the most relevant. So yes, this is a very important window. It is important to check this in regular times, just so you don't have anything fishy going on. Yes, on the top there are some summaries of all the draw calls, dispatches, clears, and blitz. Blitz are the update sub-resource calls, by the way, and the copy resource calls, and one present, obviously, which is presenting the bug buffer to the screen. A command list executes would be relevant if you are doing deferred device contexts rendering for multiple threads. It can improve your CPU time if you use them wisely. In my case, I'm not using them right now, but this is available in my engine as a experimental feature. So yes, the other things I'm not really sure of what they mean. So yes, let's close this and move on to profiling. So I will bring down the range profiler window. I set it to full screen for easier readability. So we are presented with another timeline, a new timeline. This is our timeline which was displayed on the scrubber window here. We can view it by event ID or GPU timescale. Well, my GPU timescale is sort of messed up. My user performance marker ranges, so this time I will use the event IDs. I hope this will be fixed too in future releases. So we can profile our ranges by clicking on them. At first we have all actions profiled. We can see profiler info in 3 different tabs or parts. The first tab shows some basic timing information. The second part is showing what are the most bottlenecks in this range, and the third one is showing your memory utilization. But of course we can bring up some details in each one of them. For example, an action details show for each API call your exact timing and shaded pixels, which are important metric. And for dispatch calls you can view also your GPU timings and instruction counts and sorts of like that. So yes, on the pipeline overview you can see range details, which is a nice diagram generated for you, which shows multiple details of your frame. The inefficiency factor basically means the bottleneck. If any of these red bars would fill up to the full, you certainly have a bottleneck in your application, and you will be warned against it by highlighting these well, any part of the pipeline which is bottlenecked in the current range. And so range table and action details, you can find other sorts of information if you wait for it a bit. So you can find a whole bunch of different data gathered for you, and this is a kind of out of scope for this video. We will see the nicer, simpler things here. So the memory utilization window can also generate a nice little diagram for you, which can show you your cache miss ratio or hit ratio, which is kind of one of the most important things really, and your memory bandwidth from different parts of the pipeline are also quite important. So now let us profile a specific range. Now I have an occlusion cooling rendering range right here. So I select this range right now. We wait for a bit, and we can see some nice details about this stage. So yes, there are no dispatch calls, so that side of this tab can be ignored, but there are some draw calls. Let's see some details about those. These draw calls are actually very fast, a couple of microseconds only. They are not shading pixels, so these are only checked against the previous frame depth of buffer, not writing anything, just reading the depth buffer. So yes, it is quite a simple stage, not many bottlenecks, quite saturated, which is a nice thing. Let us just see another range. For example, a shadow map rendering stage should be a bit more interesting. This range is one of my shadow cascade renderings. This renders the whole scene into or at least which can be seen from the sun shadow, one of the sun shadow cascades. So part of the scene is rendered to depth buffer only. And as we can see, this shader stage is highlighted on this diagram, showing us that this could become a bottleneck, because it is quite heavy on the shader side, especially on the vertex shader side, which is quite strange. It actually most of the time is pixel shader, but in this shadow pass for many of the draw calls we don't even use I don't even use pixel shader, just vertex shader. I only use a pixel shader if there should be alpha testing and whatnot. So we can see that memory bandwidth is actually not high because because our cache efficiency is quite high. So as we can see on the memory tab, we have a near an excellent cache hit rate. So the cache line gets evicted quite a few times, which is very good for performance. Yes, this can most likely be not improved anymore. What I need to do, or what someone would need to do if she wanted to optimize this part of the rendering, is probably see what kind of shader bottlenecks are there. So probably there are some math operations or some texture operations taking place in the shader side, but actually I know that the vertex shader side is only math operations for me. So yes, blending and Z buffer is also quite heavy because we are writing a dev buffer and reading it also, and rejecting samples which are occluded. So yes, let's see, for example, a compute shader profiling data. So in the middle of the frame I have some compute shaders. Most notably, this is the light cooling compute shader. This is just a helper compute shader, which is very fast, but this is actually quite heavy. So I select this specific shader by clicking on it. It gathers the profiling data, and the pipeline overview. I am warned again that this shader yes is quite likely to be bottlenecked, or the pipeline is bottlenecked by this shader, which is of course because this is a quite heavy shader and not very optimized yet. It has many mathematical arithmetic operations, many memory operations, and quite bad on the cache miss rate. So it misses the cache quite a high amount of the time, which could be improved certainly by using different data types, memory layouts, and memory access patterns, which is quite an advanced topic. So profiling a single shader can be very helpful, as you can see, but you can profile also your user ranges, which is also very helpful. For example, I could even profile the whole shadow map rendering phase, which consists of directional light shadow maps. There are also omnidirectional shadow maps, which are rendered into cube maps, and the whole range can be profiled and the data gathered about. So as we can see, also the shadow map rendering is quite nice on the cache, which is a very good thing. And our main scene rendering is well, not so much, but it is still very good. It is bottlenecked by the memory, by the cache and the texture operations, and as we can see, the pixel shader operations are also very heavy on the whole rendering process. So yes, there's another interesting thing which I want to show. There is another kind of timeline right here. This interface is a bit clunky, I think, but it gives us some very interesting details about the rendering process. This is showing us the GPU work scheduling. So these gray lines are actually draw calls here. These are in my occlusion cooling render phase, because if I click here, then this will be highlighted as blue. And we can see that the driver has scheduled our draw calls to be run concurrently in parallel, which is a very good thing. But dependencies in the pipeline can alter this behavior. So, for example, if I have a dependent draw call somewhere in the pipeline apart from these, then that draw call cannot be scheduled at the same time as these. So there will be some GPU stalls potentially. And yeah, of course we can see some of that. Most notably here, this big line is stalling the whole unit, and further draw calls are waiting for it to complete. Let me see if I can click on that, and oh, no. So yes, you should avoid dependencies in the graphics pipeline. And for visualizing dependencies, Nsight also can help you a lot, actually. Let's see our dependencies. So I close the profiler, and on the scrubber window we have a dependencies markers. So we can see for this draw call, for example, which is a main scene rendering draw call, it is dependent on this compute shader, which is a light cooling compute shader, and several draw calls are depending on this draw call. So and this also depends on the shadow map rendering. So dependencies mean that a certain resource, for example, shadow map rendering generates shadow map resources which are bound to the graphics pipeline after the shadow map rendering has completed, and this pass uses actually those resources, so it is a dependency on that range and those resources. It can be easily visualized, it is very helpful, and so yeah. What else? Okay, so I think that covers it. We can, by the way, we can just go back to, oh, so I can go back to this Nsight HUD, and actually I just can resume my frame capture and continue my application from where it left off. So yes, I have captured the frame and continued the frame, and the whole application continues to run, and it is quite a nice interface. I think other graphics debuggers can't really do this. This is my favorite graphics debugger at the moment, even if it has its mistakes, downsides, but the NVIDIA constantly updates this debugger, so this, all in all, I like this very much, but it is also problematic to use it on other hardware than NVIDIA. For example, if you have an AMD graphics card, you can use it with reduced efficiency. You cannot view, for example, profiling information and some of other information. But AMD has their own has their own graphics debugger called AMD Perf Studio. There is also Microsoft programs called, well, there are two Microsoft graphics debuggers. One of them is Pix, and the other is integrated into Visual Studio, actually. They're also kind of nice. Oops. Okay. Oh. It is also, by the way, strange that before capturing an Nsight frame, you just have to press Ctrl Z, which in my case is also the undo button, like this, so I can capture a frame once again. It can be a bit weird, but nothing to worry about. So yes, I think this is all. Basic information for Nsight. Yes, I want to do more rendering breakdown videos and in the future for released games. I also a lot of people actually asked me for tutorials, graphics programming tutorials, which I am considering doing in the future. So I think that's all for now. Thanks for watching. Stay tuned, and you can subscribe if you want. Like the video or dislike it if you didn't like. So yeah, thanks for watching. Take care. Bye.